Now, once we've got the acceleration, we can then just treat our electron as a projectile. So let's look at its motion. So we have a positively charged plate up here, a negatively charged plate down here, and we have our little electron, which initially is traveling at a speed of 4 by 10 to the 6 meters per second squared. And there's an acceleration we worked out in part 3 towards the positive plate, because the electron is negatively charged, of 7.025 by 10 to the 13 meters per second squared. Now, that acceleration is perpendicular to its velocity, its initial velocity, at least anyway. Okay, the velocity is initially horizontal, the acceleration is up vertically. That acceleration is going to have no impact on the horizontal component of velocity. So what we have to do next is we have to kind of look at the two components of the motion. So we have to look at the vertical motion and the horizontal motion and split those two things up. Now, if we look at it horizontally, this is its initial velocity, and there's no acceleration in that direction. Okay, there's nothing that's going to speed it up or slow it down. So we can actually just use speed equals distance divided by time to answer this part. The speed is your 4 by 10 to the 6 meters per second. The distance that it has to cover is the 100 millimeters between the plates, which is just 0.1 of a meter. And we're trying to work out the time. Rearranging that gives us that the time is 0.1 divided by 4 by 10 to the 6. So we get a time of 2.5 by 10 to the minus 8 seconds. You can see those electrons are traveling really, really fast. It's going to take them a very short amount of time to cover that distance. Final velocity of the electrons is a little more complicated, because if we look at the path those electrons are going to take, this horizontal component is going to stay constant. Initially, its vertical component of motion, its vertical velocity, will be 0, but this acceleration is going to increase it. So after a while, it's going to take a parabolic path, and at the end, its velocity will have both a horizontal, draw that again, component. So by the time it gets to here, it will have some velocity, something like that, and it will have a horizontal component and a vertical component of velocity. But of course, this component doesn't change because the acceleration is only acts in the vertical direction. So what we're going to do is we're going to separate those components of motion out, and we're going to first look at the vertical. Okay, so initially in the vertical direction, u is 0. We're trying to find out what it will be after this time here that we worked out in the previous part. The acceleration is what we worked out in part 3, I think it was. And yeah, the time we've got from part 4. So we just simply use v equals u plus at, v equals 0 plus your acceleration multiplied by the time, and it gives you 1.756 by 10 to the 6. But what we have to remember is that's just the vertical component. We still have the horizontal component of motion, so we know that this is 1.756 by 10 to the 6. We know that this horizontal component doesn't change, so it's going to stay as 4 by 10 to the 6. And we're trying to work out that resultant. Okay, so just using Pythagoras' theorem then, it's going to be the square root of 1.756 by 10 to the 6 squared plus 4 by 10 to the 6 squared. Type that all in your calculator and that gives you 4.369 by 10 to the 6 meters per second. Question 6 then asks us to find the final direction of the electrons. What we're looking for then is this little angle in here, and we can just do it underneath the question. Tan theta equals opposite over the adjacent. The opposite is 1.756 by 10 to the 6 divided by the 4 by 10 to the 6 gives you theta of 23 degrees. Last question then is the vertical deflection of the beam. So we know it's going to take a path something like that across the 100 millimeters. And what we want to work out is, okay, if there wasn't any electric field there, it would kind of go straight ahead. But what is this displacement essentially? Now that is a vertical displacement, therefore we just look at the vertical components of the velocity. So initially here the vertical component of velocity is naught. We're trying to find out what s is. We know from before that the time it would take to transverse at 100 millimeters is 2.5 by 10 to the 8, and our acceleration is 7.025 by 10 to the 13 meters per second squared. So we can use s, the displacement, equals ut plus a half at squared. Remember, we're only dealing with the vertical direction at the minute. Use 0, so we kind of drop that first term. Is equal to half times 7.025 by 10 to the 13 multiplied by the time, which is 2.5 by 10 to the minus 8. Remember to square that. And it gives you displacement of 0.02195, which is roughly, let's just round it to 22 millimeters. Now what that means in this case, if you're asked to comment on your answer, is if we go back to the original diagram, it would actually take a path something like this, because if you remember, this is 25 millimeters, so if by the end of it our electrons are 22 millimeters from the center point, that's less than the 12.5 millimeters they have to play with. So in fact this beam would head into the top plate.